Welcome to Abstract Synthesis, where we share the stories behind interesting academic papers in the world of program synthesis and symbolic AI. This is a podcast from AGI Research Lab and DIA. I'll be your host, Brian Landers, and in this episode today, I have the pleasure of speaking with the author of a paper called PoE World, Compositional World Modeling with Products of Programmatic Experts. It's a bit of a mouthful, but we'll call it PoE World probably most of the time. You may recognize him from our recent Live at NeurIPS 2025 episode where he jumped in, but this is going to be a much deeper dive into his paper. So without further ado, can you please introduce yourself?
Hi, my name is Top Piriyakulkij. I'm a fourth year PhD student at Cornell, advised by Kevin Ellis. And I work on symbolic world models and in human-like AI, human-like learning.
Ooh, exciting. This is hot topics these days. Couldn't be more exciting stuff to cover. Shout out to Kevin Ellis. Thank you, Kevin, for introducing me to Top before NeurIPS, because I asked him if he was going to be there and he's like, no, but Top, my student is going. You should definitely talk to him. So appreciate him. And also just he's been a real superstar in the world of ArcAGI, which is the benchmark our founder, Francois Cholet, created. So maybe we'll get into that later, but thank you, Kevin.
Thank you, Kevin.
The other thing, before we dive in, also, I just got to give you two huge props, Top. Number one, the writing of the abstract in this paper is like one of the best I've ever read. I went to just kind of, prepare for our talk today, and I was just like, this is like what every introduction should be for a paper. It's like crystal clear, and you make complex things seem simple, but also really exciting. Huge props for that.
Yeah, it's actually mostly thanks to Kevin and Marta, who really made that abstract look really, really good. They're really good at writing.
Like, okay, just a little taste of this. Like, here's a quote. Learning how the world works is central to building AI agents that can adapt to complex environments. Mwah. Beautiful. So that was really cool. Just like fun to see great writing. So, everyone out there should read the paper just as an example of that. But then also kind of a new trend I've been seeing are these really fun landing pages, like usually on GitHub, for the paper to kind of promote it. And it's sort of like a high level abstract before you dive into the nitty gritty of the technical parts of the paper. And yours, especially because it's got some really fun, like a video of, the AI playing, Atari games or whatever, which is just really fun to watch. So props for that one too.
All right. Thank you. Yeah. We thought like we were writing a paper where like the results on the paper look cool, but like the cooler things are like the things that we're actually seeing when we're working on the projects and all these like videos of the agent playing the game. So we were like, okay, we should totally make a video and put it on the landing page so everyone could see the same thing that we did.
It worked. It's very effective. All right, let's talk about the paper, PoE World. Give us, kind of a high level, what's the sort of elevator pitch? What is this paper all about?
Sure, yeah. So, let's assume that you want to build a world model of an environment, and you want to build it quickly with very little samples. So then traditional narrow world model with neural nets just wouldn't cut it, right? Because it would just take a lot of samples to learn a reasonable neural world model. At the same time, if you look at symbolic world models, it seems like it might work with very low sample, but it's at the time we were working on this project, it's only been shown to work on very simple domains like grid worlds. So the question is, how do you come up with a symbolic world model or neuro-symbolic world models that can scale up to these more complex domains? And our idea is pretty much, instead of trying to synthesize a gigantic program, a single gigantic program that explains everything to be a world model like previous symbolic world modeling approach, we'll instead synthesize a bunch of these little programs, which we call programmatic experts. We'll attach weights to it. We take a product of it, and our final world model will be a product of programmatic experts. And it turns out that this kind of world model can scale up really well with like more complex domains. It's able to this kind of system is able to output really sophisticated and stochastic world models. So yeah.
That's great. Okay, I'm following. One thing we skipped over, though, I think we should cover just for folks, and I'm still kind of warming up to this, world models. It's actually like, sounds fairly simple. Like, you have a concept of the world and you know how to operate in it. But how do you, in sort of your world, define a world model?
I think it just it's our understanding of the environment. One thing that a lot of people have been doing these days is to trying to build like a literal copy of the environment. So trying to literally build a simulator of the target environment and call that a world model. And it is also what we do in this paper. I actually don't think that is what should be our understanding or like the agent's understanding of the environment. I think you want something that is more abstract. So something that's more like an abstract world model. And maybe to give a very concrete example in this sense is, for example, if you're an agent and you have to plan to go to, say, an airport that takes like a 4 hour long drive, if you have to simulate um, the possibility, simulate like the environment frame by frame, then you have to generate like a 4 hour long video at the very least, right? And we
Yikes.
haven't even talked about how like there are
Yeah,
like many possible futures, and you have to branch out.
for
Um,
sure.
yeah,
Agonizing.
so that just sounds really expensive and not the way that we think about that us humans think about like whether I can go to this to an airport or not.
Yeah. The Waymo will
I
never
think
show up, ever.
yeah, I think the right way to think about it is that like you have a skill to that you can drive anywhere close enough to your current location, given say a Google map, and you can mentally simulate that in a single mental step. That if you choose to drive to this airport, then you be at this airport, and you might not even know what this airport look like. So you might not even know like the actual like what the actual final frame is going to look like, but things like that you're going to be at the airport, that the time will be roughly in the evening, and all these like more abstract informations that you have. So I think that's okay. I've talked a lot about abstract world model, but essentially I think when we talk about world model, that is the direction we should move in towards. We should think of it as kind of like a useful mental model of the environment that will help us efficiently plan and then eventually take actions.
This makes sense. And just to kind of, reflect my own sort of understanding of this is like, okay, cool. We've had, AI, we had agentic AI where they're kind of doing things in like software land. Now it's about like trying to get them to like take action and understand like interactions in whether that's, again, more software or like real world, even like robotics. And do they require some sort of concept of like their own environment and how their actions might impact results and things like that? Almost like adds like a temporal aspect where it's like I do this, something happens, there's like a time frame and stuff,
Yeah.
Predicting like, what do I think will happen when I do this? Humans innately understand so much about like physics and objectness and all these things. So all that to me is kind of encapsulated in this sort of world model conversation. And it seems like a holy grail type thing where like, we're going to have to figure this out to unlock truly awesome, like humanoid robots, for instance, or even just, like probably AGI, like general intelligence that can kind of, do things like humans can do. So very, very important and very exciting, but also sounds very like sci-fi and stuff too.
Yeah.
Question for you, you are able to kind of record your AI. Part of the paper was like actually like, watching, gameplay essentially, right?
Yeah.
Would you say is like one surprising thing that the AI system can do after watching like less than a minute of gameplay?
There's this one thing. So maybe let's talk about pretty much like the first sign of life that we got when we're working on this project. It was actually not something we showed on a landing page. So I think we also didn't really mention it explicitly in the paper. But it's that when we were able to literally use the world model as a simulated and as a simulator to the game, and I interact with it in real time. So you could actually use the world model as like a game simulator, and I was actually playing in it. And the world model was small enough that it could respond in real time. So I was like playing this a very similar version of the game, but simulated with the world model. And that was actually really cool and like the first sign of life of the project. And we were like, okay, this is working to some extent.
That's fascinating. It's almost like you were kind of playing inside the imagination of the system or something,
Yeah,
right?
yeah, yeah.
I mean,
Yeah,
not literally, of course, but
yeah. Which usually, I guess, if your world model is too big, then you don't get to do that either, because then like it would just take forever to respond to you, to like simulate just one step. But luckily, like the games we were working with and our world model were like just small enough that like it runs in real time, and I was pretty much able to play it. And that kind of helps us like understand like what the system can do and cannot do, and debug all these things too. So that, yeah, using the world model as a literal game simulator was the really cool uh milestone we got at some point.
I love that. That's super cool, and props for scoping it down enough to kind of get those results. That's a bit of an art within research. So huge props. Okay, paper. The story behind it. Every paper has got context. The people working on it. Sounds like you're working in Kevin Ellis's lab. The work
Yeah.
that you did before to kind of get there. What is the kind of story behind PoE World?
Before we started the PoE World project, I was working on this project that is pretty much about how do you learn. It's concept learning, and how do you actively learn a concept. So a concept might be something like, for example, say if there's like a scene, if there like a configuration of blocks, then you have a concept that says like, if the majority of block is red, then it's like a positive configuration. So those kind of concept. Um, so and the reason why we were looking at that kind of domain is because it almost like captures how everyday science kind of works. So suppose like there is a ground truth rule that positive scenes or positive configuration of blocks will it's positive if the majority of blocks is red. But at first you don't know about that rule. And then say you just given like a positive example at first, and then you have to just try to construct a configuration of blocks, scene of blocks, and then ask an oracle whether that is positive or negative. And then you just keep doing this until you kind of nail down the actual what you think the ground truth rule is. So that is essentially kind of like a small example of everyday kind of science, although in a very limited context. So that's what I was working. And after we wrapped up that project, then I started to think about, okay, now that we have this kind of like system that can um, do active experimentation and come up with hypotheses, can we now look into like a more RL kind of domains, where you actually now have to where your hypotheses now will be well modeled, right? Where the environment is very complex, and your hypothesis is going to be a lot more complex than something like majority of block is, right? Um, at first, I was just kind of thinking about, okay, now that we decided we want to do this kind of like agents and learning world models and do active experimentation to nail down the right world model. Um, we were thinking of like what domains should be, what exact domain should be we be working with. And
Mm.
Kevin Ellis, my advisor, um, he never tells me to explicitly work on Atari and all these games, but just like in some random meetings, he would just like show me that, hey, like Atari, there is this benchmark or like an environment called OC Atari, where it's Atari but someone make it work so that you be given bounding box for all the objects. But I'm not telling you to work on it. He didn't even say anything. It was just like, oh, this is really cool. Like now you can do symbolic world modeling on it because now you can have symbolic inputs and life is a lot easier. And I've heard he just shown that to a lot of people in the lab too.
It's like a pet passion.
Yeah. And he never really tells us that like this is what we should work on or anything. And he just say, oh, this is so cool. So that then one day I just like thought back about that random meeting that I had with him, and I was like, oh wait, there's this game, Montezuma Revenge. A lot of people seem to care about it, and it seems like a really. And I was feeling ambitious at the time. I was like, okay, well, we're gonna solve this. Like we're gonna solve Montezuma Revenge for good. We didn't end up solving it, but we didn't make
Good
some
progress,
so.
though. Very good progress,
Yeah.
and surprising results. That's a good step.
That is a very, very Kevin thing to do. Like he never tells us to work on things. Like he just kind of like
He plants the
float
seeds.
the ideas by. Yeah.
It's like, it reminds me of like parents when they try to like say to their kids like, oh, broccoli is so cool, you should totally try, and it's like,
Yeah.
This is a much better example of that, where he's actually
That's exactly what he did.
he's influencing, the choices. But in this case, it actually is really cool, and it's sort of an exciting, visual thing and conceptually, but it also constrains the world in a way that, like, I think is very intuitive because people have played games, or and a lot of folks have sort of had experience with that. So it's actually kind of a brilliant, thing, even though it's very sneaky the way he sort of subversively mentions things. I love that. Was it world models that you were like, I'm gonna work on world models, or was it like, I'm gonna solve this like AI challenge that people haven't solved yet, and I'm gonna be ambitious about that?
I think it's a little bit of both. Like I think we have we do want to solve something that people can't solve before. But at the same time, like we are looking for the kind of problems that people haven't solved before. That would be kind of like a good testing ground for the kind of tools we'd like to use. In this case, it's like a more symbolic kind of world models. And so object-centric Atari was a really good fit for this.
Understood. Okay, that's super cool. Before we dive into the paper, which I'm kind of dying to do because it's just such a fun topic, were there any other contributors that you want to mention? Like who was a sort of important, who played an important role in the paper? Obviously, Kevin, we've mentioned. Is anybody else co-authors to mention?
Yeah. There's Yishao, one of the co-authors who helped a lot with like just looking at my messy code base and make it less messy, and getting the RL baseline to work. There's Hao, who also helps with setting up the world coder baseline. So Hao is the Augur world coder, and so he really helps with that. And lastly, Marta, who's really helps with writing. I think a bunch of some of these quotes in the paper, some of them are from Kevin, and some of them are from Marta.
I love it. And this,
Yeah.
like I said, it's really good writing, so that shows. It's great. You could have totally taken credit for that, but you're sharing the sharing the attention. You mentioned when we spoke at NeurIPS, kind of setting expectations for people. Like you explicitly don't model pixel level appearance, right? And because we're talking sort of I'm trying to remember the symbolic world models, I guess is sort of how you described it. So
Yeah.
what observation interface like do you assume for the work here, and like how much do you think that assumption mattered?
So we assume that instead of taking in like pixels as input, we take in a list of objects where the objects are described by like the object type and like the bounding box. So the location of bounding box, width and height. But yeah, so this list of bounding box is a lot list of objects, list of bounding boxes is a lot more high level than pixels, obviously. So it is a very important assumption, and it's definitely hard to relax this assumption as well. I think it's like an active area of research on like how would you discover objects, and all this kind of stuff. One thing that's when talking about this, then like some people might think that, okay, then perhaps like all we need to do is like try to come up with like a universal object detector, and then run it every time you have this like pixel inputs. But what we discovered while working on these projects is also that like that what should be seen as objects should it really depends on what kind of task you're doing. So there is no such thing as like a universal object detector either. So it's it's definitely still like a very open problem, and still a very hard problem of like how do you discover these like um, essentially higher level representation of of a scene given a task.
Okay, this makes sense.
Yeah.
What was that expectation that you think people had? So just to say it explicitly, it's like they think it's visual input and then just turning those into concepts and then, sort of reasoning from there. Is that sort of the assumption?
Well, I think when people see Atari, then people thought that we're just working directly with pixels.
Okay.
Um, yeah, and then we're just had to say, well, we're not working
Yeah,
directly with pixels, but
got
if
it.
you are able to get these high level representation, like like turns it into like a list of objects, then you can do this like very efficient, very sample efficient world modeling. You can plan in it and do this like really cool stuff with it.
Yeah, this makes sense. And topic of the show is program synthesis. That is a component of this is creating programs which sort of represent or encode the world model. You could say. What made you confident that like lots of tiny programs plus weighting, which we'll talk more about, could kind of scale to Atari game complexity?
I was confident when it worked.
Yep.
Or
Okay.
I wasn't confident when it wasn't working. Or we just
Awesome.
kind of we started with like symbolic, like just like a single program as a world model. It didn't work, right? And then we're like, okay, it seems like the one of the thing that it was just made it not work too well is like when you try to refine this like single program world model, the refined program just looks so much different from the earlier world model, and it just like some of the things that I was already getting right, just got refined and it became wrong. And so we thought that like, okay, that is no good. And what we probably want in these world model is some sort of modularity where the things that are already right and quite irrelevant to the things that are wrong at the moment should just be modular. So yeah, I think we're um, we were not confident until it worked. But when it worked, it worked.
Yeah. This makes me think also, it's a good segue to the next thing I wanted to ask. You mentioned before there's no universal concept identification, thing out there. There's also not, you don't want to like cook all of the sort of, smarts of the system into like one, expert, if you will. And this is a known concept, is to kind of break things up into different domains. And that's a good time to kind of introduce this, the namesake of the papers, PoE is Product of Programmatic Experts. Can you introduce us to these experts? What are they?
Well, they are. You should think of it as pretty much causal rules or causal laws about the environment. And so each of them being like one little rule and law about the environment. And when you have a bunch of these and then you combine them, uh, it can give you a pretty sophisticated looking kind of world model. To give a concrete example of these experts, um, an expert might look something like, if you're on a platform and you press left, then you should move left. But if you're on a platform and you're trying to go down, you're trying to move down, you won't move down. Your feet won't sink into the platform. And then you might have a different expert that say, oh, but if you're on a ladder and you're trying to move down, then you would move down. So just a bunch of these experts. Some of them are even almost contradicting, but just eventually it just kind of adjusted by the weights, which I learned from the data that we see. then it's able to give you a mostly accurate world model.
Very cool. One concept I've heard is this kind of like, it's like a mixture of experts. Is there a difference between like a product versus like a mixture of experts?
So I think when you trying to have these like smaller things combine into like a bigger things, um, when you have this like concept of product is really good, because it seems to preserve modularity in the sense that, for example, if it have one expert that is outputting uniform distribution, and they have another expert that's outputting like a really a non-uniform distribution, some sort of distribution. When you multiply the two distribution together, then you just get the ladder distribution. So the uniform distribution wouldn't do anything. Um, so it seems like by taking a product, it seems like it has some sort of this like modularity kind of property that we want. And in the paper, I have this kind of figure where like when you take a product of these distributions, one way that you can kind of think of it is like layering a heat map over like say the possible locations of objects.
That is super cool, by the way. And so to kind of weight more toward this, do this more frequently, or it's more likely to be correct. The programs are more likely to be correct here, you know?
Yeah. Yeah.
Oh, that's really neat.
If you do addition instead of a product, I'm not sure if you're gonna get the same kind of like having one expert like expressing essentially no preference by doing uniform distribution. Because then if you add uniform distribution to another distribution, then the final distribution won't just be the ladder distribution.
I see.
Yeah.
Almost was required to like make it work in this case. One thing I feel a bit like new in this world, but you kind of cited this concept of like mind as community of experts. Where does that concept come from, and how literally did that sort of shape the algorithm?
It didn't shape the algorithm in any.
It's a cool idea.
In any tangible way. Well, but so the cool thing is like it seems like we're converging on the same ideas as these other people that's like been there for a long time.
Say more. Yeah. What is that idea, and how does it map here?
So it was Marta who cited this paper. So Marta Marta is our like cognitive science kind of person. So she knows about all these references. I think that was the work from Marvin Minsky, who's like a really big AI person back in the days.
Gotcha.
But I think, but it didn't influence the work in any tangible way. But it is cool to think about how like we are converging to like the same kind of ideas about modularity and this like community of or set of experts that a lot of people in the past have talked and thought about.
Okay. I mean, you don't want to get in a fight with cognitive scientists or whatever, but like it was a cool idea to think of like all these competing, like say a neuron represents this like logical assumption, and then almost like, something like this, product of programmatic experts happening in the human brain. But we don't need to get into that. We don't need to start any fights or pick inappropriate metaphors.
Yeah.
One thing that caught my eye was this kind of exponential weighting. Your experts are weighted exponentially. What intuition should, we have, as we're reading this paper for what the weights mean?
You should think of it as something that's controlling. So if you think of each expert as expressing preference over, say, like possible locations of an object or of a player, then this weight is essentially pretty much controlling the strength of how strong of a preference it is. And in an edge case where the weight is 0, then it's pretty much going to turn the distribution into like a uniform distribution, and then it is expressing no preference. So it's just no preference. And then as your weights get bigger, then it's the expert is expressing more preference. So just again, it's just I just kind of think of it as this like layering of heat map, and the experts with low weights will just the heat map will just the intensity of the color will just be low.
Okay, got it. All right, before we dive deeper into just, how this system that you created works and the cool results that kind of came from there, and then eventually even the reactions of everyone at like NeurIPS and other places to the work itself. These Atari games, Montezuma's Revenge. By the way, do you know that like the meaning of Montezuma's Revenge is not a cool thing?
Does it mean like diarrhea?
Diarrhea.
Or yeah.
While traveling. Anyway, that aside, this is the name of the game, but this is actually like a well-known kind of challenge, like within the AI community. Like, why do people care about beating this particular Atari game?
It's because it's the hardest. Well, first of all, like Atari was like a really standard benchmark in reinforcement learning. A lot of people were working on it. So it's a very popular benchmark. But there's this one game, well, maybe one or two or three games that just really, really hard. One of them, or like the most popular one being Montezuma Revenge, where even until now, people still don't really know how to solve it in a very sample efficient way. And part of the reason why this game is so hard is because it is a really hard exploration game. And hard exploration game means to get a reward in this game, you have to take a very complicated looking kind of action sequence before you can get the first reward. While if you compare that to Pong, there's like a much higher chance for game like Pong where there are like two paddles and you like trying to hit the ball. There's a much higher chance of just randomly scoring in Pong by just taking random action sequence. On the other hand, with Montezuma Revenge, it's a lot harder to just do things randomly and get a reward. But at the same time, you as a human, when you play this game, it's almost obvious to you where you should go. There's a key, and there's this like you can try to go to the key.
A ladder.
Yeah, to using some of these pads, and people are able to get to the key very, very quickly. So that is kind of like a puzzle there. Like what is missing in these reinforcement learning algorithms? Like, why does it seem like, and if anything, Montezuma Revenge for humans is like easier than these other games that reinforcement learning methods are doing well on. So then the question is like, why is that the case? What are we missing, and how do we make our algorithms explore better or explore in a more human-like way?
Oof, big problem. I mean, pretty challenging, and lots of people have tried different things. That's super exciting. It's very bold to choose that challenge. So again, huge props for diving in there, being ambitious. Let's talk about the kind of nitty gritty of how it works. I guess what I would pick up would be this kind of like learning pipeline. So walk me through this. There's kind of a loop, like demonstration. You have like LLM kind of generate like candidate programs. Again, this is program synthesis happening here, and then I guess you kind of go through like a refinement, part of the loop. But correct me if I'm wrong. Like break this thing down for me.
Yeah, we actually don't do any refinement in this work. Although I'll explain that you can do a refinement if you want to. But yeah, so we first assume that there's like a demonstration of someone playing the game. In this paper, it's just me playing the game for 1 minute. So technically, we're not really tackling like directly the exploration problem just yet. But assuming that there is this demonstration of a gameplay for like a really short one, like a minute demonstration, then the learning pipeline is that we're first going to ask LM to generate a bunch of these experts. So we prompt LM to generate a bunch of these experts. The experts we make a few assumptions to essentially turn these experts into distributions. And now that you have a bunch of these distributions, we attach this like exponential weights to it. And the weights are learned by doing gradient descent to maximize lock likelihood, given the demonstration that you've seen. And so when you were talking about refinement, you could totally do refinement. So right now we're not doing any refinement in the sense that we just throw data to the prompt for LM, and it would just output experts. But you can definitely have like a more complicated looking kind of synthesis model to come up with a more complicated experts. You might have like a synthesis module that takes like several refinement iterations with LM so that you get like a really complicated looking kind of experts. It turns out that for at least for the domains that we were working with in this paper, we didn't need too much of that. So we're just kind of stick with like a simple looking kind of experts.
Makes sense. Okay, I think I kind of get it. Whenever I hear about like, LLM generation of programs, I wonder like, in a system, like what happens like when things go wrong. So like, how do you prevent like LLMs from hallucinating kind of, like causal rules that sort of look plausible, but like actually don't at all like work in the game?
Yeah. I don't know.
Yeah, I don't know either.
Yeah. And so in this work, we're pretty much taking advantage of the fact that in the domains that we're working with, that most of the time the LMs will at least give out reasonable rules in the sense of like reasonable cause and effect. And even if it's wrong, then like when it's wrong, then it doesn't explain the data, and then you get rid of it. But it's not like something like some spurious correlation, like if you touch the ladder, then the ghost moves. Then right? That sounds like a really not like a cause and effect kind of thing at all. And LM is smart enough to know that. So that being said, if we have to deal with something like Arc AGI3, where it's going to be a lot harder to take advantage. Well, there's not going to be much prior knowledge in LM anymore, right? Then we really going to have to think hard about how to do the right causal inference. But luckily, in this work, we don't have to deal with too much of that.
Okay, that makes sense. Fair. What about another way things could go wrong, when the experts disagree? Just kind of a nuts and bolts thing. Like you mentioned, they almost can seem contradictory sometimes. How does that just get resolved through, the distribution, or how does it work?
Yeah, so that is totally fine. So when you have experts that disagree, well, eventually, if there is one expert that is wrong, and when you have enough data to prove that it's wrong, then we optimize the weights, and that experts will eventually have like a weight of 0, and then you just take them out of your set of experts.
They get fired from the crew.
Yeah. But one of the cool thing that you could get from this product of experts is also that it's also something like, suppose in the game, when you have a player and when you press right, and your player will 50% of the time move right by 2 units, and 50% of the time move right by 3 units. You can have two experts when the first one say it will move right by 2 units, then the other one saying you move right by 3 units. And even though the experts are kind of contradicting-ish, but both of them, each of them explain the data kind of like 50% of the time, and then it will just get assigned after you optimize the weights. Then your final weights will probably have the weights of the two experts will probably be roughly the same, and then your final world model is very stochastic, even though your experts is very deterministic.
Okay, makes sense.
Yeah.
I spoke recently with about like VLM, vision language programs on top, like separating reasoning from vision language models. We spoke a little bit about it earlier, this kind of like object detection, pixel sort of world model,
Mm-hmm.
Do VLMs have anything to do with your work, or do you see that kind of being integrated in future?
You could definitely try to use VLM so that you can, given the pixel inputs, then you can try to extract these like higher level variables, like for example, like XY position of a player, for example, using VLM given like a pixels, right? I think one thing that we're gonna need to figure out is that like it's gonna get very expensive very soon if you have to call VLM every time you need to evaluate these features. So I know that in our lab but I wasn't involved in it. But there's this work called visual predicator, which is pretty much you synthesize. So a predicator is pretty much like a program that will just give you a predicate value. Uh, for example, are you on a platform or not? Or a player is a player on a platform or not. So then you can synthesize these programs that will actually call these like classic computer visions tool, and they might be neural nets, right? So it might call like classic object detector kind of model, and try to output whether, say, a player is on a platform or not. And not having to call VLM every time you do this is gonna be it's gonna save you a lot of cost. Um, but yeah, I think I'm currently not sure how far that just kind of like um synthesizing this like visual predicator could go. I think in many situations you probably just want to rely directly on VLM, but that is going to be expensive. So yeah, I think there it's an active area of research. People are still trying to figure it out. And yeah, there seems to be a bunch of cool works coming out of it, and I've been following them closely.
Very cool. Yeah, it makes sense. I mean, some of these things feel like tools at your disposal to kind of test, within your experiments. You could just plug them into your pipeline somewhere. So it makes sense you're following all that. Just also conceptually really cool too. All right, let's talk results, my friend. In the paper, you claim like 4,000 plus line programs,
Yeah.
the synthesized program that generalizes to zero shot, like solving novel levels, like within Montezuma's Revenge. Is that correct? Is that what the result
Yeah,
was?
yeah.
Woo! That seems pretty impressive. Like, was that surprising?
So the generalization part actually wasn't surprising. So essentially, we have like Atari games, and then we make like these like alternate versions of the game, which still kind of follow the same causal laws of the original game. Um, and yes, we were expecting it. The world model learned from the original game to kind of apply to the alternate version of the game. We were expecting it to generalize. It did generalize. So I guess it wasn't surprising in in that aspect. But the cool thing about it is the fact that after all that it's not surprising because of how so many of these machine learning models are not generalizing in the way that we expect. Right? Like we have so many machine learning models that are not generalizing in a human like way, and we keep questioning like why
Ah,
is it generalizing this way.
the jagged
But
intelligence thing, where sometimes it's like
yeah,
right on, and then other times it's like, why can't you do this very simple
yeah,
thing? Okay.
yeah. On the other hand, for this work, we have this world model. It does generalize in the way that we expect. So it's not surprising, but it's a win for us, I think.
Well, that's super cool. And then you mentioned RL like earlier. Are there places where PoE World kind of beat, RL, specifically like sample efficiency you mentioned a couple of times. And so I'm guessing that's one spot. Was there anything else that comes to mind?
Maybe like a first caveat is that like PoE World itself is like a world modeling system, so it doesn't talk too much about like how you're gonna take actions.
Okay.
So you could still do something like running a model-free RL on the world model, like pre-training on the world model, and then fine-tune it in the real environment. Um,
Okay.
so
Gotcha.
you could wholly do something like that. In terms of like comparing to like this like symbolic model based decision making with either RL or like a planner compared to like a more traditional model free RL or like even model based RL. I think it does, because of how good our world model is given such a limited samples. Um, it's a lot more sample efficient in the domains that it works. Um, but when you have this like symbolic input and you can do symbolic world modeling, then it really is a lot more sample efficient than these like prior methods. But what PoE world is currently not generally not good for, or symbolic world model in general, is the flexibility of it, right? Like when you have a neural net, you can literally like for any kind of inputs in any kind of domains, like just literally throw a neural nets at it, and you might be able to run it. Usually, if you run a model free RL long enough, then you might get something out of it. But when you have this kind of like symbolic world models and symbolic methods, for if you have to deal directly with pixels, for example, then life is really hard and it just doesn't work. Um, so I would say that in situations that it works, then it's really good and it's better than these prior methods. But there are many situations that it's not working, and that is what we're currently working on, trying to expand the range of tasks that it does work.
Okay. That makes sense. Thank you for breaking that down, and also just the clarification that it's not like RL versus like, PoE world. These things are complementary. You mentioned earlier ArcAGI-3. That is the next iteration of the abstract and reasoning corpus for artificial general intelligence benchmark. Before it was sort of 2D kind of static grids. There was input output, and each task had a few examples, and then a couple outputs that became the test. Whereas ArcAGI-3 is going to introduce a sort of temporal angle, and they look a lot like these Atari games that you were working on. The only thing that's special about any Arc benchmark is that every single task, or game in this case, is different. So no matter how you master it with RL on one game, you're going to be totally having to figure it out fresh for the next one. What do you think are going to be like the limitations we'll start seeing when we launch the benchmark next year?
Limitations of
current systems. So even throwing like RL, with models, maybe even, or PoE world, for instance. Like any work you're thinking of throwing at V3.
I think the traditional RL kind of method, or at least model free RL, is not going to work well, because it seems like essentially when you trying to generalize to this novel environment, it's just not going to work. It seems like for ArcAGI-3, you really need a model that's trying to understand what's going on in each of these games, and model free RL having the reputation of literally remembering action sequence to get things to work probably won't work too well. At the same time, things like PoE World, and we were already talking about this a little bit. So not just PoE World, but currently there are a lot of methods that are relying on LLM's prior knowledge. So we are kind of cheating in the sense that like we're just use this like super powerful LLM to give us the right feature, right rule, propose the right thing for whatever we're doing. It's going to be a lot harder to do that for ArcAGI-3, which just because of how the game is designed, then there's just going to be less prior knowledge in the LM that you can take advantage of. And so I think that the task then is a ArcAGI-3 that is then really focusing on like this like ability to like rapidly learn to generalize to these new environments, and you can't cheat with LM anymore. So
There you go.
that's exciting and also scary.
Yeah, I mean, this is the slogan. Sort of one slogan of ArcPrize Foundation is new ideas needed. Like AGI remains unsolved. So it feels like kind of the spirit of what you're saying. All right, so everybody get ready for this. Top's gonna be working on it, I can tell. There was something, felt at the end of the paper kind of like a pointer toward future work, but it was about exploration.
Yeah.
My favorite quote about this in the paper was, efficiently exploring the world is analogous to testing the program that encodes the world model. So you were focused on this in this paper with kind of that encoding of the world model, right? In a sort of symbolic way. Where do you see this like exploration, phase going? And is that something you're thinking about working on?
Yeah, it's something that I'm collaborating with some collaborators on. Although I'm not the one leading the project, but it's like, if you remember, the way that we started this project was that we were going to do active learning and and we're going to do active exploration and come up with world models. But we didn't get to that because like just coming up with world models itself are already so hard. So we're like, okay, I'll just assume a learning demonstration. Um, but yeah, I think so. So one of the directions in terms of like explicitly taking advantage of the fact that now you have like these like programs as your world models, how can you do like a more efficient exploration? Um, and I think Armando's lab at MIT is already working on this. So just kind of like
Oh,
trying to look at the structure of the program to see like where to explore.
very
Um,
cool.
so I think they're already have some work on this. In the context of something like PoE World, you can kind of think of this as like, for example, if you have a prior on the weights of the experts, so you might be uncertain about like what the weights of say this particular expert is, and say this expert, let's say that it's about what happens when a player is touching a skull or a ghost. Um, then if you have high uncertainty over this program, over the weight of this program, then you can ask like, okay, what kind of action or sequence that I can take so that I can try to reduce this uncertainty, for example. If you have a program that, if in the program of that expert, it says something like, if a player touch the skull or ghost and something happens, um, then then you know that you want to test that if condition essentially. So that's where like the idea of software testing comes in. So you want to be able to go inside of that if condition. So then the kind of experiment you should do is to get the player to touch the ghost or the skull, which would be a good exploration.
That's really cool. Yeah, and it's could almost counterintuitive because it's almost like playing to fail or something. Like it may not be the most optimal path through the game, but like,
Mhm.
it's worth
Mhm.
learning like what happens. And I think
Mhm.
humans do this. Kids definitely do this. Like they will
Yeah.
repeatedly fail just to kind of
Yeah.
see what happens.
Yeah.
Um, That's neat. That's really cool. Yeah, I mean, again, just cool writing in the paper to kind of frame that up, and definitely felt like, a prompt to folks if they're interested in this work, like, what threads to pull to kind of keep it going. Speaking of other people in the world looking at this paper, what was the reaction from the community? You did a poster talk at NeurIPS, had probably hours and hours of conversations with people. How did it go?
Yeah, it's mostly good. I think people are excited about the fact that, wow, you can get the key and you can get a positive reward in Montezuma events so quickly. Um, I guess there are some people who are like, yeah, object detector is going to be really hard to get. Your work doesn't deal with that yet. So not impressive just yet. And we're like, yeah, that is fair as well.
The
We'll
critics.
keep working on it. We'll keep working on it. But I think most of them are pretty positive. I think people seem to like this direction of um, thinking about how to come up with a more complicated looking kind of world model.
Yeah, I love it. Just combining this sort of symbolic stuff, with the sort of
Yeah.
model side is really cool,
Mm.
and lots to be explored there. And just the results are pretty cool, so they speak for
Mm.
themselves.
Mm.
That's great, and props for just getting selected to do that. I know that that's a hard thing in and of itself. So, in addition to publishing a paper and doing all the work, getting to share it is pretty cool. So,
Mm.
I think you shared some ideas about, when I asked you about the exploration thing, about what you're working on. Is there anything else you can share about what you're thinking about, actively working on now?
I think roughly what I'm thinking about now in terms of like world models is to eventually go into do something that looks more like an abstract world model that we talked about at the very beginning of the podcast. So something like, how do we not have to generate a 4-hour long video to plan to get to an airport? Um, so that's like a world model that's temporally abstract is going to be very important. And it also seems like the kind of skills you have, for example, in this like example of driving to the airport, your world model, your understanding of the world also depends on what kind of skills you have. Um, so if you have the skills to drive to an airport, then you have the understanding of I can drive to the airport, and I'll be at the airport.
Lot in there.
Yeah, so temporally abstract world model and just kind of like unifying this like both like understanding of the world and the kind of skills or actions that you can take is I think is a very exciting direction that I've been thinking about.
Okay, all right. It's a bit of mystery there. There's a lot of space to explore. All right. Well, I'm gonna definitely keep in touch with you and follow up and see what more I can glean about this. It sounds like cool stuff happening in Kevin's lab. So excited to follow you. Any advice to folks, just starting to check out the symbolic side of AI, like, and even specifically, program synthesis? Like, what words of advice would you give people or pointers?
I don't feel like I'm qualified enough to give advices to people. I mean,
You
just
are.
do.
You absolutely are. You've created this wonderful paper that exemplifies neurosymbolic
Yeah.
work, and so that is a cutting edge thing, because we've got these new wonderful tools with LLMs that we can now combine
Yeah.
with AI, the old school AI. So
Yeah.
you're absolutely qualified, but also it could be just like, what have you learned yourself, doing it? Like, were there any sort of challenges where you like, oh, this is actually like a very promising direction, or like, nah, I'm over it. Symbolic stuff is boring. It could be anything.
One of the things that would be really exciting to move towards is like a more neurosymbolic kind of world models. I think obviously you can't do everything with like a fully symbolic programs. So just figuring out how to like merge or bridge that two worlds of like first the neural worlds and the symbolic worlds would go a long way.
Very cool. Yeah, I think that's exciting. So everybody go check that out. Definitely go check out Top's paper. PoE World landing page also to watch the AI play against Montezuma's Revenge, like we spoke about. Just huge props on the paper, Top, and congrats for presenting at NeurIPS. Thank you for joining us, and I can't wait to have you on in future for whatever you get up to next. We really appreciate your time.
Yeah. Thank you so much, Brian.